Hello everyone, welcome back to AP Physics class. Today we will be deriving simple harmonic motion from circular motion equations with me. Let's get started. So first of all, we need to understand what circular motion is. Circular motion is a movement of an object along a circular path. As the name suggests, an object that is moving in a circle is basically what circular motion is. Let's take a look at this diagram drawn by yours truly. In this diagram, we can see that the object is moving in circular motion because it is following a circular path. Moving on to simple harmonic motion. Simple harmonic motion is the repetitive movement back and forth through an equilibrium where maximum displacement on one side is equal to the maximum displacement on the other side. Now, this definition might seem hard to understand at first, but I promise that it's really not that hard. Take a look at this diagram. We can see that this object is moving in simple harmonic motion because it is moving back and forth, passing an equilibrium point. In this context, the equilibrium point is the center of the path that this object takes. As it is moving back and forth from left to right and right to left, it is passing the center, and its distance from left to right is equal. These two concepts are actually very connected with each other. As you can see in this diagram, when the object is moving in circular motion, the object's y-axis is moving in simple harmonic motion. And this is the same with its x position as well. As the object is moving in circular motion, its x position is moving in simple harmonic motion. Now that we understand those concepts, we can start deriving equations for simple harmonic motion. Looking at the diagram, as an object is moving in circular motion, we can take its angular displacement by looking at the angle between the initial position of the object and its final position. We can relate this to the x position of the object by looking at the cosine function. Cosine theta is equal to adjacent over hypotenuse, and in this context, cosine theta is equal to the x position of the object over the radius of its circular path. We can also isolate the x position by changing the equation into x position equals cosine theta multiplied by the radius. However, we need to find the x position in terms of time. So what can we do? Well, we can look to another circular motion concept known as angular velocity. Now, angular velocity is equal to delta angular position over delta time. And delta just means the change in or final minus initial. So we can rewrite that as angular position final minus angular position initial over time final minus time initial. So let's just assume that the initial position of the object is 0 and the initial time is also 0. This means that we can turn the equation to angular velocity equals theta over time. And we can isolate theta to become theta equals angular velocity times time. Now we can just put this back into our previous equation, and our new equation becomes x position equals cosine angular velocity times time multiplied by the radius. Now let's go back to circular motion. As mentioned before, angular velocity is equal to delta angular position over delta time. Now, delta angular position can also be interpreted as one full rotation of an object along a path. Now, one full rotation is also equal to 360 degrees, or in radians, that's 2 pi radians. Meanwhile, change in time, delta time, or change in time, for one full cycle is also known as a period, which can be labeled as capital T. This means that we can change the equation for angular velocity to equal to 2 pi radians over a period. And since 1 per period equals frequency, we can change that equation again to become 2 pi radians times frequency. Now we can just resubstitute angular velocity in our previous equation to 2 pi radians times frequency, and the new equation will become x position equals cosine of 2 pi radians times frequency times time multiplied by the radius. Now let's pay closer attention to the previous diagram. In this diagram over here, we can see that as the object reaches the max distance in its y position, the distance is equal to the radius. And at the same time, at the position versus time graph, we can see that in the wave, it is equal to the amplitude of the wave. This means that the radius is equal to the amplitude of the wave. This is the same in the x position. Now, knowing that the radius equals the amplitude, we can resubstitute the radius for amplitude, making our final equation x position equals cosine of 2 pi radians times frequency times time multiplied by the amplitude of the wave. But wait a second. If we're using cosine, shouldn't the graph look like this? This is what a cosine graph looks like, right? Then why did our graph look like this? Isn't this a sine function? And you are correct. Because in the example that was given before, since we are looking at it in the y-axis, the object is actually starting in the equilibrium position. In order to use the cosine function, we need to make sure that the object starts at farthest from the equilibrium point, meaning that it's starting at its max position. Meanwhile, if the object starts at equilibrium position, we can use the sine version of this equation. This is because when the time is equal to 0, when we use the cosine function, the cosine of 0 is 1, meaning that the x position of the object will equal to the amplitude or the radius of the circular path. This means that if we are using the cosine equation, when time equals 0, the position of the object has to equal the amplitude or its max position. Meanwhile, if we are using the sine version of this equation, the sine of 0 is 0, meaning that the x position of the object at t equals 0 is 0, which is the equilibrium point. So, if the object starts at equilibrium point, you use the sine function. However, if the object starts at farthest from equilibrium point, you use the cosine function. But what if the object doesn't start at either of those? What if it starts in between the equilibrium position at the farthest position? Well, then we will need to consult phi in order to phase shift the graph according to the initial position of the object. However, we will not go that far in depth in this video, so we'll just leave it at these two equations for now. Thank you so much everyone for watching. I hope that this video helped you understand these concepts easier, and I hope you guys have a nice rest of the day. Thank you!